Oh, thanks, Greg. So I'm Henry Segerman. This is all joint work with Jeffrey Irving, who's not here. He works at a company called Other Lab, which is in San Francisco. What's a fractal curve? So people first sort of started thinking about this around the 1890s, and there were these examples that Peano was the first one to come up with one of these examples of functions from the unit interval, say, into a two-dimensional shape, say a square. So these space-filling curves where, this raised questions about what dimension means. You've got a one-dimensional thing, a line segment, which is mapping into and, in fact, filling up the entire inside of a two-dimensional thing, a square. This is the Hilbert curve. Hilbert came up with this maybe a year or so after Peano. Well, this is the construction of the Hilbert curve. So there's a distinction to make here between the fractal, the space-filling curve itself, and the steps in the construction of it. So here, this is a sequence of just polygonal curves. So these are not fractal in themselves, but the implication is that as you move further on, this curve gets squigglier and squigglier, and in the limit, with some well-defined notion of what limit means, you end up filling the entire square. But we're going to be interested from the sort of artistic point of view in these steps in the construction of the fractal curve. So here are a few examples. So this is some iteration. Again, I may just say this is the Hilbert curve. It's not. It's a step in the construction of the Hilbert curve, but just insert those words, step in the construction of, ahead of anything that I say. So the Hilbert curve, this is Hilbert in 1891. This is the Sierpinski arrowhead curve, which limits onto the Sierpinski triangle, which, as far as I'm aware, is due to Mandelbrot in 1983. The dragon curve, due to Highway in 1967, was when it was published by Martin Gardner, I think. And the Tur-dragon curve, which is due to Davis Knuth, 1970. So how do you come up with these? How do you formalize the shape? How do you generate these things? So a good way to talk about these things, something called an L system. L systems were introduced by Aristid Lindenmayer in 1968. He's a biologist. He was interested in how do you sort of algorithmically grow plant shapes. And he came up with this idea. It's called an L system or an L system grammar. So there's three parts to this. You have an alphabet, an axiom, and a set of replacement rules. So we're going to do the L system for the Tur-dragon curve. That's this one down here. So we have an alphabet. This is a set of letters that you can use in building up a word. So there's only 3 letters in this alphabet, F, plus, and minus. There's an axiom, which is the first letter that you start with before you do anything else, and that's just the word F, consists of a single letter F. And then there's a replacement rule. In this case, there's only one letter that gets replaced. The letter F gets replaced by F minus F plus F. Plus and minus are other letters that can appear in your word, but they don't get replaced by anything. So what do? We start with this axiom, F, and we apply the rule. So our first word is F, our second word is F minus F plus F, and then we again, anytime we see an F, we replace it with F minus F plus F, and if we see a minus, it just stays there, and if we see a plus, it just stays there. So okay, so you build up these sequences of letters. What do you do with these things? So now you interpret this sequence of letters as sort of turtle graphics instructions. So F means move forward 1 unit, minus means turn right by 120 degrees, and plus means turn left by 120 degrees. So this is the first one. F just means start somewhere facing some direction and move forward. And the second one, F minus F plus F, so what am I doing here? I move forward, I turn right by 120 degrees, I move forward, I turn left by 120 degrees, and I move forward. Now notice I've sort of changed the rules a little bit. This moving forward 1 unit, this unit is shorter than this unit. And I've also changed the direction that I'm facing at the start, and the reason for both of those is that I want the start and end points to match up, because otherwise these pictures are going to get very large. I want to fit them into the same size. Do it again, F minus F plus F, and so on. And you can sort of already see some of the self-similarity that's, again, the fractal curve itself is self-similar. Each of these curves itself is not self-similar, right? There's no, what does self-similarity mean? It means you can take the whole design and scale it down and fit it onto a part of the design. You can't do that with any of these. But there is a sense in which the set of these curves is self-similar, because I can take this whole design, scale it down, and put it in place up here. And you can sort of see why that's working with this replacement rule, where here there was, well, right, this whole word here appears as a subword here, and so it makes sense that you should be able to do that. Right, so, well, I'll get onto this more in a little bit, but there's a lot of issues to do with how do you draw good pictures of these. And I'm already starting to cheat in a way. I'm not following my rules, right? If I was following my rules, this would be a polygonal curve. But I've got these little curves, or these little arcs of circles down here. I don't know if you can see that. And the reason that they're there is that, well, let's just show what happens. So these are 4 different ways of drawing these same sets of curves. You can't really tell the difference here, except that this one's very thick for some reason. Let's go to the second slide. So here's the difference. So this one up here, this is actually doing what the Total Graphics program tells you to do. And this one is introducing these tiny little rounding off at the corners. If I go a couple more slides forward, you can see what's going on with these different cases. So the green guy up here, I've got these little arcs of circles, so you're turning the corner, and the reason is that if you don't do this, you can't tell what's going on. You can't tell where the path goes just from a single picture. So you want to round these corners off and get this picture. But there's a problem here. So it looks pretty good around here, but as I move forward, you can see that these shapes here are getting kind of blobby. And the reason for this is that the radius of curvature of these little circles isn't changing as I'm increasing the level of recursion. And so at some point, this is going to fail, right? If I go a few more steps further, then the line segment length here is going to be shorter than the radius of curvature of the circle, and I'm not going to be able to continue. So this looks nice up here, but then it starts breaking down. So this guy here is an attempt to fix that. And here, the radius of curvature of the circle is sensitive to the length of the line segment that we're following. And so this works much better. There's this annoying stuff here. You don't really know which way you're supposed to turn, so you have these little straight lines at the start and end point on this version. And we're losing something as we're doing these alterations. What happened to our self-similarity, right? So over here, we have this pattern here, zigzag here, really is this thing scaled down. Well, more or less, I'll come on to why it isn't in a second. Whereas here we've got these annoying endpoints. So it's sort of difficult to actually retain all of the properties that you really want whilst having it be able to see what's going on. And then what's this fourth guy here? Well, so there's another reason in which we're going to fail as we keep getting smaller. And the reason is that the thickness of the lines here is not sensitive to the length of the line on them. And so eventually, as I keep going, these lines will crash into each other and it'll just be solid red. And so over here we have the thickness of the lines sensitive to the length of the line segment. And so this is I think this is as good as you're going to get if you're not willing to just stick with the original one like you should do, perhaps, and not see how the path winds its way through the vertices. Okay, so where am I going to next? So if you wanted to show this sequence of slides, well, you could either show the slides or you could show a sequence of pictures, or you could show an animation. So you could step through these pictures, say 1 second at a time, like this. And I'll come back in a sec to why we didn't do that for the sculptures. So the idea of the sculptures is, take this sequence of this animation, and instead of viewing it as moving through time, have it move through the third dimension. And that's really what our contribution was, and the rest of this talk and the rest of the paper is just sort of messing around with how you actually do this. And so what's going on? So we're roughly speaking using this version or possibly this version. I'll get into the difference between using one of these 2 different ways to draw this in a second. But what's happening up at the top here, there's the single straight line. There's the first level of recursion, and then actually 2 windows down is the second level of recursion, the single zigzag, and then another 2 windows down. It's a little hard to tell, but somewhere in here is the third level of recursion, and so on. Now, let's see. So, do I want to go on? Yes, I do. So we want to retain as much of the self-similarity of the sequence of curves as possible. And so this is a different sequence. This is the dragon curve rather than the turdragon curve. So I won't give you the L system for this. It's a little bit more complicated, but I'll just mention what you do. So one way to view this, you start with a strip of paper, and then you fold it in half, and then unfold it, and you get a 90-degree angle here. And instead what you could do is you could fold it in half, and then fold that in half again, and then if you open it out so that everything's 90 degrees, you get this picture. And if you fold in half, and then fold in half, and then fold in half, and then open it out, you get this guy, and so on. So we have this again, this self-similarity between these between these pieces. So this guy here appears down here as half of the guy at the next level. And so if we were doing this as an animation, you might want to show 1 frame each second. And if you were doing this, then the distance between these different levels would be 1 second, or well, whatever your unit of distance would be. And this is not what we've drawn here. And so the difference is this height, you can see, is a little higher, is a little taller than this height here, the difference between these horizontal positions. And the reason for this is because you can make the surface self-similar as well. So we have to interpolate in some way between different levels of these curves. So what we've done here is just very simple. So I've got one straight line up here, and these two guys at right angles here, and we just filled it in with the simplest polygonal thing you can do. So in this case, I've got a 45, 45, 90 triangle here, another 45, 45, 90 triangle here, and an equilateral triangle here. And you want to do the same thing down here at this next level when this edge here gets bent at a 90-degree angle here. And in order to have the angles all be the same, that's why we have to scale this down here. And so you can figure out what the scaling factor is by looking at the length of this edge compared with the length of this edge, and you want to scale down the change in height by whatever that ratio is, something to do with square root of 2, presumably. So that's the basic thought, and then we started doing a bunch of stuff with it. So this is the turdragon curve. There are a bunch more choices in how you represent these things. So as I think, as I said before, there's sort of 2 sets of windows here between one curve and the next curve. And so what is this middle strip in here? It's just some sort of interpolation. I won't get into the details of what it is. The reason why we have 2 windows rather than just one is that if you just have a single big window in this face, then you sort of don't see the surface so much. Why do I have windows at all? That's a good question. Why not just have a solid surface? So again, this is an aesthetic choice. Well, it's also a financial choice. It costs less money if you have punch holes in the thing. So it also, it makes the surface slightly transparent in a sense. You can see through it to things on the other side. And it also shows you something about the parameterization. In this case, it shows you something about where these curves came from. Even though they're smoothed out and interpolated, if you follow it down, you can find, this doesn't work. So I'm going here, and then I'm trying to pull back, but the laser point isn't moving back, but you know what I mean. So I go here, and then I move back, and then I go here. So that curve there, that zigzag, you can see it because of the windows. So this has 2 windows for each level, and goes to, yes, how many levels is this? Any guesses? It's probably 6 or 7 levels of recursion. This is 1 level further, and this is a large version of the print that was in the, so we had an exhibition at the Simon Center for Geometry and Physics that closed a few days ago, so too late, so you can't go and see it now. And this idea of putting a mirror underneath it was somebody, not me, but it was a very good idea. It means you can sort of look from above and see the pattern underneath as well as seeing the surface itself. So this is the Hilbert curve. I believe this is also two levels of windows for each pair of subsequent curves in the sequence of curves that construct the Hilbert curve. Sierpinski arrowhead curve. Sometimes you get these interesting things. So there's all of these faces here that now that I've told you that there are faces there, you'll never be able to unsee them. They're all of these clone troopers, perhaps. I'm not really sure. Just came out of the mathematics, honest. And this is the dragon curve. This one is only one window per level. And I mean, the choices of how many windows to put in was somehow related to how much longer is the next curve down. I mean, if you're going from a short curve to a very long squiggly curve in one jump, then you want to put in extra levels of height to really see the distortion. Whereas here, the scale, the length here to here is only going up by a factor of square root of 2. So it's not so bad. Somebody described this as looking like an office building going for a walk, which I kind of like that image. It's a strange office building. I'm not sure I'd want to work there. I'm almost done, and I have lots of time, but anyway, so Jeffrey and I, we actually sort of independently worked on different ways to create the geometry for these things. All of these things are my way of doing things, which were sort of, well, brute force interpolation of Bezier functions and very complicated. Jeffrey took a very different approach, which in some ways makes a lot more sense. Let me just explain what he did. So we go right back to this picture here. So he started with just this very simple polygonal mesh. And then he wants to subdivide and smooth the mesh. And so there's something called loop subdivision, which I won't get into, but it's a way of, it's a method of taking a mesh and then smoothly subdividing it. It has some very nice analytic properties. And so that's what he did. He just started with this very simple mesh and then started subdividing. And because it's so clean and algorithmic, the way that he's doing it, he's actually able to retain some self-similarity on the nose. So these pictures here, I mean, in a sense, it's approximately self-similar, but the way that you have to interpolate and sort of curves interact with their neighbors, and it all gets very complicated. So who knows how much of this is actually self-similar? Oh, I should mention, right, particularly, so the thickness here. So I was going to talk about this. Thank you for reminding me, Henry. So I think this is the better thing to do in a sense, right? This guy here, where it's sensitive, the thickness is sensitive to the length of the line segments that you're using. The problem is that you're trapped between, up at the top, it's going to be immensely thick, and it's just going to be solid plastic. It's going to be very expensive, and it isn't really going to look very good. So if you scale everything down, then at the bottom they're tiny and fragile, and they're going to break. So this is, I'd like to be able to use this, but I think somehow it's not possible. So in fact, for this model here, it's slightly thicker at the top because you've got this sort of big area that you need to cover. And if you've got a very thin sheet with a big area to cover, then it's not going to work so well. It's going to be fragile. And so it sort of linearly scales down by a factor of 2, going from the top to the bottom. But that's just, you have to deal with what you have. I mean, I think, right, there's a lot of these, getting a little bit philosophical, there's a lot of these issues of when you're trying to illustrate something which is a curve, it's one-dimensional, it doesn't actually have any thickness, but you have to draw something. So how do you deal with the fact that you have to thicken up, and then it causes all of these problems? And in 3 dimensions, you have to thicken up in many different directions, and causes even more problems. Anyway, so having done with that aside, so Jeffrey did the correct thing, because he doesn't have to print it out, he just has to show renders. And so it's really very thick up the top, and it's very thin down the bottom. And this coloring is telling you the actual self-similarity between patches. So when you see all of these light blue patches, they really are self-similar to each other on the nose. So this guy at the top isn't self-similar to anything because there are boundary effects. But as you get further down, you see all of these patches of exactly the same. And I think, right, so you see these yellow, I guess I've got a pointer, but it's probably a little small. This sequence of yellow blocks down here, and then you see the same thing repeated inside, going down further and further, presumably forever. So that's my talk. Thanks very much.